Let's get started with setting up a simple model that demonstrates some of the key features of Simulink. In this session, I'm going to show you how to create a model starting from scratch, how to simulate it, and how to quickly refine and make the simple model into a non-trivial model of a hybrid system. You can start up Simulink by clicking on this icon right here in the MATLAB toolbar to bring up the Simulink library browser. The Simulink library browser contains a library of over 200 standard blocks. The standard blocks can model continuous systems, nonlinearities in the continuous systems, can be used to model discrete systems, perform math operations on signals, route signals, organize systems and subsystems using hierarchies, etc. Additional application and industry-specific block sets are available within Simulink. For example, the aerospace or the communications block set or the control system toolbox allows you to model aerospace or communication systems or control systems. The data acquisition toolbox and the image acquisition toolbox allow you to bring in data from live sources into Simulink. Real-time workshop and real-time workshop embedded coder allow you to generate C code from Simulink models that can then be targeted to specific processors using the target block sets. For example, you can target the MPC 555, the TIC 2000, the TIC 6000, etc. Using sim events, you can perform discrete event simulations within Simulink, and Stateflow allows you to model finite state machines within the Simulink environment. The Simscape platform allows you to model mechanical, hydraulic, or electrical systems within Simulink. Additional verification and validation tools like Simulink verification and validation allow you to continuously verify and validate your design throughout the development process at the model, code, software, or hardware levels. So let me start with a new model here, and then drag a sine wave from the standard sources library, an integrator from the continuous library, and a scope from the standard sinks library. And I can connect up from the output of the sine wave to the input of the integrator, and click on the integrator block, hold down the control key and click on the scope block to automatically create a connection between the output of the integrator to the input of the scope block. So what I'm doing by connecting the output of a block to an input of another block is creating a flow of a time varying signal from a source to a sink. By connecting the outputs of one block to the input of another block, we form a mathematical relationship between the connected blocks. These lines that connect the blocks are what we call signals, and they are time varying quantities. While time is not explicitly shown in the Simulink model, Simulink integrates time into its models, meaning that everything in the model is exercised by Simulink's timing engine. Each block essentially has a set of equations that can be solved as a function of time. This distinguishes Simulink from C, for example, in that it is a high-level language providing a canvas to simulate the dynamics of a time-varying system without having to write mathematical solvers for the time-varying part. The blocks thus provide a set of equations as opposed to an operation that might be provided by a high-level programming language like C. So let me now save this model at this point. Now let's look at this model in a little more detail. Connected up some blocks, but we don't really understand what the integrator is doing, and we're not sure what the parameters are. So let's double click on the integrator block. Double clicking on any block in Simulink brings up the parameters dialog box for that block. The parameters for every block are different, and if you look through this dialog box here, we can see that the integrator has an initial condition, has options to limit the output of the integrator has an option to turn on saturation port or to turn on the state port. But let's see what all of this means for the integrator. Clicking on the help will bring up the help browser with more information about the parameters and this block. So here you can see the equation that the integrator block models, how you might define initial conditions, how you might limit the integral, how you might reset the state of the integral, and how you might use the integrator block within your own algorithm using standard examples. Key point here is that all Simulink blocks in the standard libraries have detailed help. So you know what you're doing and you know how changing the parameters will affect the simulation for each block. Let's close out the help and come back to this. So we know that I'm integrating the sine wave that has a value of 0 at time 0, and we know that integral of sine 0 is minus cosine 0, which is minus 1. So instead of starting with an initial condition of 0, I'm going to set the initial condition of the integrator to minus 1 and say OK. Save the model and click this button to simulate it. Double click the scope to bring up the output of the scope. So you can see that the integral of the sine wave is a cosine wave as we expect. You might say this is a very simple task, and what advantage does Simulink provide as opposed to doing this in C? Well, even for the simple example, Simulink has provided you a quick way to develop your system model without writing your own solver. Even writing a simple Euler solver would take a significant amount of time, and what Simulink has allowed you to do in this case is model your algorithm or the math of your system without having to focus your energies on writing a solver. Now let's go ahead and add some more complexity to this model by making it nonlinear. And how I might do this is add some saturation to the output of the integrator. Now let's simulate this nonlinear system and look at the output. As you can see, even with nonlinearities, the simulation time is almost instantaneous. Another key feature of Simulink is the ability to work with signals in parallel. So let me try and show you how this is possible. I'm going to drag and drop a gain block onto my signal, and instead of using a gain of 1, I'm going to use a vector of gains. So what I've just done is now multiplied the output of the integrator by 8 gains starting from 3 to 10. And at this point, Simulink provides easy visualization of which signals are vectors and which signals are scalars by turning on some of these displays. So you can see that this signal and the output of the integrator is a scalar value that then gets multiplied by this gain, converting it into a vector value of 8 signals running in parallel that goes to the saturation and remains the same. Now, this is still fairly trivial, and I might make this a little more complicated by changing the saturation limits. So instead of using fixed saturation limits, let me use random saturation limits between -10 and 10, for example. And what I'm doing here is using the rand function from MATLAB to generate 8 random values between 0 and 1 and multiplying that by 10 to create the upper limits, or 10 random upper limits, and doing the same thing to create 8 random lower limits between 0 and -10. So let's simulate this model and look at the output. Let's simulate this a couple more times here. And if you zoom in to a portion of this, you will see that the signals are saturating at random values and at random points in time. And the Simulink solver is able to capture this accurately and precisely without having to take small time steps. This shows you the efficiency of the Simulink solver in it being able to capture the dynamics of the system without having to take small time steps. If you wrote your own solver, you might spend a lot of time either optimizing the solver, do this, or the solver itself might have to take very small time steps to capture the dynamics of the system precisely and accurately. Simulink also provides you a bunch of different solvers that you can use when modeling a system. In addition to the default solvers, let me show you the other solvers that Simulink has. Clicking on Simulation Configuration Parameters brings up the Configuration Parameters dialog box. Here you can set a start time and a stop time, for example, and you can pick between variable and fixed step solvers. You can also pick different kinds of solvers, for example a discrete solver if you're modeling a discrete system, or a bunch of different continuous solvers, including a stiff solver for stiff systems. But I'm going to use the default solver with the default options and say OK here. Well, so far we've modeled a continuous time system. Let's try and modify the system so that now it is a hybrid system. A hybrid system contains both continuous and discrete states. So I'm going to drag in zero order holds into my model, and zero order holds are basically a way of sampling the signal. I'm also going to modify the scope to now display 3 axes so I can view all the signals in parallel. Expand the scope right here, save the model, and set the sample times. Double clicking on the first zero order hold brings in the parameter dialog box for this. So instead of specifying a sample time of 1, I'm going to specify a sample time of TS1. For the second zero order hold, I'm going to say sample time TS2. Now TS1 and TS2 are not defined, but if I define these two variables in the MATLAB workspace, Simulink will pick these values when it's simulating the model. And this is a feature called data-driven modeling that Simulink supports. Data-driven modeling allows me to specify values in the MATLAB workspace to drive my Simulink model and parameterize the simulations. So by modifying these values in the MATLAB workspace, I can look at the output of the simulation for different conditions without having to change the model. So let's simulate this and take a look at the outputs now. Now in this system, Simulink also provides easy ways to visualize which of the signals are continuous and which of these are sampled. So I just turned on the sample time colors, and you can see the black lines in the black blocks represent the continuous parts of the system, the red lines represent the fastest sample signals, the green lines in the green blocks represent the next fastest sample signals, and so on and so forth. If you look at this block diagram now, you might say that it also looks a little messy. So what I'm going to do is use some of the features of Simulink to make this block diagram look a little neater. So I'm going to select these blocks and line them horizontally, redistribute them so that it looks a little neat. Change this block a little. and move this block around so it looks a little. Well, so far we've seen how to implement an algorithm using Simulink block diagrams. So now let's say that you had a pre-existing MATLAB algorithm that you want to implement in your Simulink model. Let's see how this is possible. Embedded MATLAB is the subset of the MATLAB language that allows automatic implementation of existing MATLAB algorithms as C or HDL code for embedded applications. The embedded MATLAB function block allows you to simulate your embedded MATLAB algorithms in Simulink. By incorporating your existing MATLAB algorithm into the embedded MATLAB function block, you can automatically generate C or HDL code from your Simulink model that also contains your MATLAB algorithm. So now, say I have this MATLAB algorithm implemented in an M file. So this might be a MATLAB function that calculates the sampling error between two signals, and this is standard MATLAB syntax. This function now contains an additional directive, the EML directive, which tells the embedded MATLAB compiler to compile this function for use in your Simulink model. Now we want to incorporate this function within our Simulink model. What I'm going to do is, from the user-defined functions block, I'm going to bring in the embedded MATLAB function block into my model. Double-clicking on the block brings up the standard template, and I'm going to modify this template so that it now calls my existing MATLAB algorithm. We know this function takes in two parameters, u1 and u2, or two arguments, u1 and u2. So I'm going to change this function to also take in two arguments, u1 and u2. I'm going to save that and close it. You can see Simulink has automatically updated the block to take in two inputs. Let's say I compare the sampling error between the continuous signal and the slower sample signal. Also bring in a scope to visualize this over the course of the simulation. Let's simulate this and look at the output. So there you can see that the embedded MATLAB function is invoking the pre-existing MATLAB algorithm and calculating the sampling error between the continuous signal and the slower sample signal at every time step, and the output is being displayed in the scope. So it was pretty easy there to incorporate existing MATLAB algorithms into my Simulink model using the embedded MATLAB function block. Now that we've gotten some level of complexity in this model, we might want to abstract away some of the details from the main model. To do this, we can create a subsystem. Subsystems allow the design to be simplified for graphical visualization while providing model hierarchy. Let's see how this is possible. So say I want to create a subsystem out of this so that I can hide some of this detail and potentially reuse that. So I create a subsystem using some pre-selected blocks. If you double click the subsystem, you can see that the original blocks that I had selected are in the subsystem, and Simulink has added in a few additional blocks like these input and output blocks. These input and output blocks provide an interface to the parent system. Let me also clean up this model a little bit at this point. Well, now that we've created the subsystem, we can change the way it looks, and we can also parameterize the subsystem if we wanted to reuse it multiple times in our model. Right click on the subsystem and bring up the Mask Parameters dialog box. Masking the subsystem allows you to change the way it looks. For example, using MATLAB commands, here you might load images or plot data. I'm going to use the plot function to plot the peaks function in MATLAB. Hit apply. You can see that the icon has changed to the plot of the peaks function. You can also parameterize the subsystem. The sample times can be parameterized. So let's say I wanted to parameterize sample time 1 and sample time 2. By parameterizing these two variables here, what I've done is created these variables in the local workspace. This is separate from the MATLAB workspace. So if I reuse the subsystem, when I bring up the parameters dialog box for the subsystem, I can set these sample times TS1 and TS2, and these sample times will be unique for each instance of the subsystem. I can also specify initialization commands that can be executed before the block is initialized. I can also add some documentation to the block. For example, I can also give it a description. And I can also give it a help. And what I'm going to do here is link to a pre-existing HTML file. Say OK. So if you double click on the subsystem now, instead of showing you the details of the subsystem, all you see is what we typed in the documentation tab and a custom dialog box with the parameterized values for sample time 1 and sample time 2. So let me say I'm going to use a different sample time from that in the MATLAB workspace. Now let's simulate this model and look at the output. As you can see, it's using the sample times defined in the mask and not the sample times defined in the MATLAB workspace. So if I change this again, also if I double click on this subsystem and click on help, this brings up the HTML file that I defined in the MATLAB help browser. So I can use this as a way to document my subsystem so that any user of the subsystem can better understand what it's doing. Now that we've documented the subsystem, we might also want to document the main model. One way of doing this is double clicking on the canvas and adding some text. You can also change the properties of this text by right clicking on it and bringing up the annotation properties parameter dialog box. You can change its foreground color, background color, alignment, etc. You could also use the text to fire a callback function. Here I'm going to open up the pre-existing HTML file when the user clicks on the text. So you hover over it, it gives you a link. Clicking on the link will open up the HTML file in the Windows browser. Other ways of documenting the model are using a doc block to add text, or adding in model info, which is a way of adding self-documentation into the model. So say I wanted to add information about the creator and the model version. This is self-documenting because every time I save it, this model info is automatically updated. So say I made a change to this model and saved it. It updates this model info and provides an automatic way of updating the documentation for the model. Decide that it's time to start componentizing it, or we might decide to componentize it before building the model. Componentizing allows different parts of the model to be worked on by different engineers, and for one to design and test each of those components independent from the main model. Let's say I want to convert this subsystem into a component. One way to do this is to copy over the algorithm into a new model. So I can connect it to my main model here. Now let's simulate this and compare the output of this simulation to the output of the original system. As you can see, it aligns from a continuous time to sample time, and let's this happened. If you double click on this model, you can see that there are no continuous parts in this model, and everything in this component can be run in discrete time. So what I'm going to do is force it to use a continuous sample time for the default input. I'm going to save this now, and I'm going to simulate this model. Let's look at the outputs, and this is exactly what the original system had as outputs. Except now it's picking up values from the MATLAB workspace for TS1 and TS2, and this is because when we deleted the subsystem, we also deleted the mask. You can right click on this and mask the model block as before and use the masks to componentize it again, and use the mask to specify the sample times TS1 and TS2, but I'm not going to do this as we know how to do it already. So far, while designing this model, we have not taken into account data types. So say for example, the designer of this component knows that we're going to implement this component on a 16-bit fixed point processor. Since we can automatically generate code from this model, we might as well design the data types for this component in the Simulink model itself. And Simulink allows you to do this. So as a designer of this subsystem, I know that I want to implement this on a 16-bit processor. And so I'm going to have to fix both the input and the output interfaces to use 16-bit data types. Let's see how this is possible. I can double click on the input block and select the signal attributes tab. Previously we'd set the sample time, but we can also set the data type. So instead of Simulink inheriting the data type, let's specify the data type. So I'm saying specify the data type to be of type fixed point. But I'm also going to use Simulink's data type assistant to decide the fraction length for the best precision. So I know this signal has a minimum value of -10 and a maximum value of +10, and I can use calculate best precision, and Simulink's data type assistant says that it needs 5 bits to capture the integer value between -10 and 10, and the remaining 11 bits can be used to store the fractional value. I can say OK. At this point, let me turn on the port data types. So as you can see, the input has been fixed to have a 16-bit fixed point value. But I also need to fix the outputs. One way to do this, of course, is to double click on each block and set the data types there. But what I'm going to do is set it using the Model Explorer. I'm going to click on this block to bring up the Model Explorer. The Model Explorer is a different view into all open Simulink models and the Simulink workspace. The left pane here shows the model hierarchy. The middle pane shows details of the model or selected block, and the right pane shows the parameter dialog box for the model or the block. So I can select this, and you can see it shows me the parameters dialog box on the right pane. So you can see here that the output data types for outputs 1, 2 and 3 are set to inherit auto, but I'm going to set it to fixed point data types based on my specification. Let me close the Model Explorer and look at this now. Let's try to run this component. As you can see, Simulink has thrown an error. It says data type mismatch. The input 1 expects a signal of fixed point 16-bit, whereas it's being driven by a signal of fixed point 32-bit. Let's look at the signals here. You can see that the input is a 16-bit fixed point number, whereas the output from the gain is being converted by Simulink to a 32-bit fixed point number to prevent overflows. At this point, I can force Simulink to keep the value data type of the signal the same instead of upgrading it automatically. Double click on this, select the signal attributes, and instead of inherit via internal rule, I'm going to select inherit via backpropagation and select apply. Now let me update this diagram, and you can see that all signals are now 16-bit fixed point, and we should be able to generate C code from this for implementation on a 16-bit processor. So let me save this model, simulate it to ensure that it runs fine, close it, and come back to the main model. Now let me try to run this main model. As you can see, Simulink is again warning you about a data type mismatch. So let's look at another way of fixing this. So we have to find some way of converting the output of the integrator from a double to a 16-bit fixed point value. I'm going to go to the signal attributes library and select the data conversion block. And I'm going to drop this block on my signal. Now let's try to run this model and look at the simulation outputs. I double click the scope, and you can see that the outputs are similar to the outputs of the subsystem, except with different TS1 and TS2 values, since these are now defined in the MATLAB workspace. So through this example, we've seen how Simulink allows you to specify as little or as much as the data types, and how Simulink can catch some of the errors that might creep into the modeling process because different component engineers have specified the interfaces differently. Now, when working with large models, simulation performance can be important. So Simulink offers a number of simulation modes that can increase the performance through the use of code generation technology. This increase in performance comes at a cost of reduced interactivity as well as additional startup time due to code generation. What do I mean here? Well, during design time or when building the model, you are frequently updating the model, needing to debug or inspect the behavior. At that point, the normal mode simulation is probably the best. When the model is built and you want to run it many times with different inputs or with different parameter values, you may choose one of the accelerator modes for increased simulation performance. While the normal mode is an interpretive simulation giving you all access to Simulink's diagnostic and analysis tools, the accelerator mode is a compiled simulation. What happens here is C code is generated from the Simulink model, and that is called from within the Simulink environment. It still has some of the interactiveness, and you can even switch mid-simulation from normal mode to accelerator mode. Rapid accelerator mode creates a separate process that runs independently of the Simulink process, and you can use this mode to harness the power of a dual-core machine, for example. This mode works well for, say, batch simulations. External mode connects the Simulink model to an external executable that has been created with Real-Time Workshop. In this mode, Simulink is basically handing off simulation to the external executable So there you have it. In this session we've created the model of a hybrid system, incorporated existing MATLAB algorithms into the Simulink model, componentized that model, and optimized it for fixed point implementation, and looked at the alternative simulation modes that Simulink has offered. Let me close down the model and hand it back to Jason.